Let me share something fascinating, and I mean that in the most literal sense. Over the past few years, headlines have been screaming that the James Webb Space Telescope has broken science, shocked astronomers, and basically upended everything we thought we knew. Now, I've spent decades studying this stuff, and I'll be the first to admit, there's a fair amount of hype in those headlines. But here's the thing, they're not entirely wrong either. Webb keeps delivering genuinely puzzling data. We've talked before about those enormous galaxies showing up way too early in cosmic history. Well, alongside that ongoing mystery, something else has quietly emerged. A researcher ran Webb's data through the ringer and found hints, real mathematical hints, that our universe might be closed off, sealed inside a black hole. How's that for a Tuesday morning revelation? So today we're going to dig into what I'd call one of the most audacious yet scientifically legitimate ideas in modern cosmology, black hole cosmology. And trust me, by the time we're done, you'll see why this isn't just science fiction. Strange as it may sound, this idea isn't new. It was born in the middle of the 20th century, right around the time physicists first realized that black holes weren't mathematical curiosities. They were real things that form when massive stellar cores collapse under their own gravity. Almost immediately, theorists started asking a question that must have seemed absurd to their colleagues. Could the entire universe be sitting inside one of these things? I've spent decades studying this, and I still find that question electrifying. Here's why it's harder to dismiss than you might think. Start with singularities. Classical general relativity tells us a black hole contains a point of infinite density at its center, a place where the math breaks down, space curves without limit, and time as we know it simply stops. Now wind the clock back on our own universe. Extrapolate backward far enough and you arrive at the Big Bang, which our best equations describe as another singularity. You know what's interesting? That's already one striking parallel. Then consider event horizons. A black hole's event horizon is the boundary of no return. Photons can't escape because space-time itself curves too steeply. Our universe has something analogous, a cosmological horizon beyond which light from distant objects can never reach us. Same concept, wildly different scale. Still think these are just coincidences? Then chew on this number, the Hubble radius of our observable universe. 13.8 billion light-years matches almost exactly what physicists call the Schwarzschild radius for an object with the same mass as everything in the visible universe. In plain terms, if you took all the matter and energy in the observable universe and asked what size would a black hole need to be to contain all of that, the answer comes out to roughly 13.8 billion light-years. That's not a rounding error. That's our cosmological horizon. And there's a bonus implication hiding in the math that I always love pointing out. A black hole's radius scales directly with its mass, while its volume grows as the cube of that radius. The logical consequence, the more massive a black hole, the lower its average density. Carry that to the extreme. A black hole with a radius the size of our universe would have a density roughly equal to the density of our universe. Now look, could that be coincidence? Sure. But it's the kind of coincidence that makes serious physicists sit up straight and at least entertain the possibility. Of course, the parallels only go so far. A black hole, by definition, is a region of space from which nothing escapes, which implies there's something outside it. But cosmology treats the universe as the totality of all matter, energy, space, and time. There's no outside the universe because the universe is everywhere. That's a genuine conceptual tension, not just a weak objection. Some of you might say that's a philosophical nitpick, and fair enough, but there's a more physical problem too. Look around. The universe is expanding. Matter and galaxies are flying apart from each other. Yet inside a classical black hole, everything is supposed to be collapsing inward toward a future singularity. In our universe, the singularity was in the past, not the future. So, if we're honest, the universe resembles a black hole running in reverse, which is what physicists call a white hole. And that's where things get genuinely speculative. White holes have never been observed. Whether they can even exist physically is an open question with plenty of skeptics. But before we throw up our hands, let me walk you through how serious cosmologists actually make this framework work. Because the expanding universe doesn't scare them at all. The most mathematically rigorous version of this idea came from Polish physicist Popławski back in 2010. His key move was to modify general relativity using what's called Einstein-Cartan theory. Here's the core difference. Standard GR accounts only for the mass of particles. Einstein-Cartan theory also accounts for their spin, the intrinsic angular momentum that every fermion carries. Spin, it turns out, can influence spacetime through a phenomenon called torsion. If regular mass curves spacetime the way a bowling ball curves a rubber sheet, then spin gives that sheet a slight twist on top of the curve. Under normal cosmic conditions, this torsion effect is negligibly small. But push matter to extreme densities, the kind that would exist at the heart of a collapsing black hole, and something dramatic happens. As density approaches Planck scale values, the spin contribution generates a repulsive force between fermions, those fundamental particles like protons, neutrons, and electrons that ordinary matter is built from. This repulsion grows faster than gravitational attraction. So instead of matter compressing into a singularity, the collapse hits a wall and reverses. A bounce right inside the black hole, rather than everything cramming down into a point, everything begins flying apart. Popławski's insight was to recognize that this bounce is precisely what we would experience as the Big Bang. In his picture, our universe is a black hole, a very large one, that never reached singularity but instead evolved through expansion. Now you might be thinking, if black holes create expanding universes inside themselves, why don't we see Sagittarius A star, the supermassive black hole at the center of our own Milky Way, doing that? Great question. The model actually predicts you wouldn't see it from the outside. Here's the trick. As objects fall toward a black hole, a distant observer never actually sees them cross the event horizon. Gravitational time dilation and redshift make the infalling object appear to freeze and fade. What happens beyond the horizon is causally disconnected from the external universe. It takes an infinite amount of external time to play out. So the bounce, the expansion, the entire interior universe, all of that unfolds on a timescale that is effectively infinite as measured from outside. For anyone watching from a safe distance, the black hole just sits there. It's a separate branch of space-time with its own timeline, invisible and inaccessible to us. This makes black hole cosmology a specific flavor of the multiverse. Every black hole in every universe spawns a new universe inside it, connected to its parent through what you could think of as an Einstein-Rosen bridge, a wormhole-like gateway between parent and child cosmos. Each child universe has its own vast timeline and can expand indefinitely. From the parent universe's perspective, it's just another black hole on the map. I've always found that image almost unbearably beautiful, to be honest. A cosmological model also has to earn its keep by solving existing problems, not just posing new ones. And Popławski's framework delivers. The bounce neatly eliminates the singularity at the Big Bang, a point that has always been an embarrassing admission that our equations break down. Better yet, the rapid rebound naturally produces the kind of accelerated early expansion we call cosmic inflation, without needing exotic hypothetical fields with unusual properties. Inflation has always required somewhat uncomfortable theoretical scaffolding. The bounce provides the same result from simpler mechanics. The obvious weakness of the Popławski model is that it requires modifying general relativity. Einstein-Cartan theory has never been experimentally confirmed. We've never detected evidence that fermion spin influences spacetime through torsion. Since standard GR has passed every test thrown at it, departing from it is not something physicists do casually. But then, in May 2025, a new and, in my view, even more intriguing version of black hole cosmology appeared, one that keeps general relativity intact. a team led by Enrique Gastañaga proposed grounding the singularity prevention mechanism not in modified gravity, but in quantum mechanics, specifically in degeneracy pressure. You know what's interesting about degeneracy pressure? It's the same force that keeps white dwarf stars from collapsing under their own weight, and it arises directly from the Pauli exclusion principle, one of the most robustly confirmed laws in all of physics. Here's a quick refresher. The Pauli exclusion principle states that no two fermions, and remember, fermions include protons, neutrons, and electrons, meaning essentially all ordinary matter, can occupy the same quantum state simultaneously. In practice, this means electrons can't be crammed into exactly the same location and state. This isn't a matter of them being too big. It's a fundamental quantum prohibition. In fact, this principle is the reason solid matter takes up space at all. Without it, atoms would pass right through each other, and the physical world as we know it wouldn't exist. Now, the universe is a place of extremes. Sometimes gravity wins and squeezes matter until particles have almost no room left. When that happens, those particles fight back with what's called degeneracy pressure, an outward quantum force. White dwarfs are held up by electron degeneracy pressure. Neutron stars are supported by neutron degeneracy. Hypothetical quark stars might be stabilized by quark degeneracy, but in every known case push them past a certain mass threshold, and gravity wins anyway, producing a black hole. Gattañaga and his colleagues argue this isn't the end of the story. The Pauli exclusion principle doesn't switch off at the event horizon. Two fermionic entities still cannot occupy the same quantum state, even deep inside a black hole. Their paper suggests there may be a deeper yet undiscovered form of degeneracy pressure, one that kicks in if electrons and quarks turn out not to be the most fundamental particles. Under that assumption, there's an absolute ceiling on density, and once collapsing matter hits that ceiling, the bounce becomes unavoidable. No modified gravity required, just the standard GR equations applied to matter with a quantum floor. What's remarkable is how much this model explains without reaching for exotic physics. The authors report that their framework is compatible with inflationary expansion. They also find it consistent with the accelerating expansion we currently attribute to dark energy. No new mysterious fields required, and they even have something to say about dark matter. During the initial collapse of matter into the black hole, regions of enhanced density could have formed primordial neutron stars and black holes. These early relics, they suggest, would be strong evidence for the model if we can identify them observationally. Now, I've been around long enough to know that a beautiful theory isn't worth much without experimental support. And here's the fundamental challenge with black hole cosmology. How do you test an idea about what's happening behind an event horizon when, by definition, no information from inside can reach you? Well, if our universe is inside a black hole, you don't actually need to look inside other black holes. You just need to look around you. One key prediction of these models is that the universe should have a slight positive curvature, shaped more like a sphere than a flat sheet. So far, the most precise measurements from the Planck satellite's analysis of the cosmic microwave background show the universe is flat, within the margin of error. The operative phrase there is within the margin of error. A more sensitive future instrument might detect an extremely small but real curvature that current equipment misses. Then there's the question of rotation. Black holes spin. That's essentially universal among astrophysical black holes. If our universe is inside one, it might have inherited that rotation. And a rotating universe should leave a detectable imprint. Galaxies ought to spin preferentially in one direction, breaking the symmetry we'd otherwise expect. That's exactly what Lior Shamir at Kansas State University set out to test, using James Webb data from the Advanced Deep Extragalactic Survey program. His method was straightforward. Look at spiral galaxies near the galactic pole, the direction perpendicular to the plane of the Milky Way, and count which way their arms curl, clockwise or counterclockwise, no spectroscopy needed. A trained algorithm can read the curl directly from the images. After filtering out galaxies whose rotation direction couldn't be determined cleanly, Shamir ended up with a sample of 263 objects. The result was striking. Among those 263 galaxies, 105 rotated counterclockwise, while 158 rotated clockwise. Roughly 50% more galaxies were spinning in one direction than the other. Standard cosmology predicts the split should be essentially 50-50 across large scales. The universe should look the same in all directions. Shamir interprets this asymmetry as a potential signature of a rotating universe, and he explicitly considers black hole cosmology as a leading candidate explanation. Now, I want to be fair here, because this is where I put on my skeptic hat. Shamir himself acknowledges an alternative explanation, the Doppler effect. Because we're orbiting the center of the Milky Way, galaxies spinning opposite to our direction of travel appear slightly brighter, which could bias our detection toward them. He argues this effect is too small to explain the full asymmetry, but the bias it introduces is real. More importantly, previous galaxy rotation studies using thousands, even tens of thousands, of objects found no statistically meaningful asymmetry. Shamir's sample is 263 galaxies. That discrepancy needs addressing before anyone should take the rotation evidence as conclusive. And even if the universe does rotate, that doesn't automatically prove black hole cosmology. Rotation and black holes go together, yes, but we'd still need to understand exactly how a rotating parent black hole would imprint its spin onto an entire interior universe and manifest as the specific directional preference we observe in galaxy spins. That causal chain isn't established yet, so where does that leave us? I'll be candid. The short answer to "are we living inside a black hole?" is probably no, or at least not proven. But here's what surprised me when I first started going through the technical literature on this. The idea isn't easy to rule out either. The numerical coincidences are genuinely striking. The theoretical frameworks, from Popławski's Einstein-Cartan bounce to Gazzaniga's degeneracy pressure model, are internally consistent and solve real problems with standard Big Bang cosmology. And there's no definitive observational evidence that kills the hypothesis. I've been teaching cosmology for a long time, and one lesson keeps repeating: the universe has a habit of turning out stranger than anyone was comfortable predicting. We spent decades dismissing black holes as mathematical abstractions. Now we photograph them. I won't pretend I know whether future measurements will reveal a tiny positive curvature or a preferred direction in galactic rotation, or some other imprint of a parent black hole. But I do know this: ideas that seem outlandish today can become the standard textbook picture within a generation. And if astronomers ever had to announce that we've been living inside a black hole all along, well, I'd say the psychologists would have a very busy decade. Some of us would find that genuinely exhilarating. Others might need a moment to sit with it. For now, we watch, we measure, and we keep asking the question. And honestly, that's the part of this job I've never gotten tired of.